think I'll give it just one more minute and then we can start. Everything's just like not super in time right now. I think we can close the doors now to start. Thank you. Okay, thanks everyone. Thank you for joining. Before I start, I always do like a quick polling. So, who of you has used NumPy before? Okay. Who of you has used pandas before? Wonderful. Have you used polars actively? Good, that's something we have in common. I also haven't used it, so that's the part we look forward to. But the rest, like, what are you doing here? You can stay here. Today is an introduction to NumPy and DataFrames. I will specifically talk about pandas and polars DataFrames. This was meant as an introductory session. This is very, very basic. I'll talk about how to interact. The goal here today is not to get you in depth into how arrays work, super user and pandas or something, nothing like that. It's more of enabling, more of getting in touch. So maybe if you are an R user or if you come, I don't know, from MATLAB, so that you have something where you can, okay, get in touch and get started. That's the goal for today. I have prepared a couple of notebooks. We'll take a look into the setup in a second. My idea would be I just walk you through here. In the end of each section, I prepared a couple of exercises. You'll probably go through them. If there are any questions, you can ask at any time. It's no problem. So this brings me to setup, if no one has questions about the scope today. So setup, I didn't know how to do it better. I prepared a repository. So this is the link here. I'm sure, I thought I could have put in a QR code, but then again you have it on your smartphones and probably not on your computer. So if you go to this website, this is my personal repository here, you can just clone it. The instructions are also written in the README. You can just clone it and go through it. Is anyone intending to do this? Really? To do it in the tutorials? Because otherwise I don't have to work it, I can just show you. Do you want to clone it and execute? Yes, no? Yes? Please try. That's what I made it for. So, also check this one here. So if you go to the repository itself, there is a README where you do find the essential steps, and you can just copy and paste them. Or for reference, again, this is the tutorial link if you want to check it out. I'll just give you 2 minutes or so to get started, and then we can continue. If you've cloned and set up the repository and started the server, it should look like something like this. Then I will start with the first part, and the first part will be NumPy. So if you have used Python before, and if you know, I don't know, the basic Pythons, you know that Python comes also with a set of operators, with lists, and you have, I don't know, sets and all of these things. They are useful for certain kind of operations, but NumPy adds on to that. So NumPy is a very specialized library, and it's by far, I think, a very fundamental one by now. And like lots of machine learning libraries were built for that. Pandas had, in the beginning, very basic NumPy init values and so on. It is designed for numeric operations and also for linear algebra, so you get a lot of like vectorized operations for that. We're not going to touch on that today, but this is what you're going to keep in mind. It's a low-level library implemented with a lot, I think, a lot of C, is it Python or C++, I don't know. And it comes with like a huge speed-up, efficiency with the data structures, and it's also in certain ways memory more memory efficient. And you'll see, I'll try to point out what the differences are to Python lists here and there, and we'll just walk through. So the first thing always is just to import the standard way is we import NumPy as NP. And the first thing I'd like to talk to you about is the array. Arrays are a data structure where you can essentially, can store data in it. Think about it less like more as a grid, I would say. So you have equally shaped grids of, let's say, numbers in this case. So in an array, you have the way to call the NumPy array is here. So you would have an object which is a grid of the values 1, 2, 3. And then there's several things you can do with them. So you can of course look into inspect the array itself. There will be keywords like there will be things like the shape that we can look into, and we can access array type, very similar to list. So if you would just have the list of 1, 2, 3, this would be the standard Python list. Let's call it just something else. You would have a very similar thing. You don't have a shape. A shape is very specific to NumPy, but you would have a length of a list where you would also see it has 3 elements here. The shape in NumPy is a bit more specific. It also tells us we have just 1 row and 3 elements. We can also access the elements in the array with, similar to Python, with just indexing. So we can also do something like L of 2. This is kind of obvious, but still let me do it. So you get it by index, you get the value. Arrays have a data type, which is homogeneous for overall the array. And this is something that lists are not. We will see that in a second as well. This is one way to create an array. Arrays are always fixed in size in the beginning when we create them. So here we pass the list object and we convert it to an array. But there are also other ways that NumPy offers. We can create it with, essentially we can say, hey, NumPy, give me an array with only ones in there. And it should be like size and shape with 1 row, 5 elements, and then we get this. This is also useful if you have, for example, like if you think of matrices, we just want to initialize with 1 and then do some matrix operations on that. This can be useful just to write it down. And similarly to zeros, so you can also create arrays where you have just zeros. NumPy offers this API. So here we specify 2 rows and 3 columns, and this is what we get. And let me just do something here. We're going to see that in a second again. Also here when we do shape, or in the ones array, if we do the shape, we just get the number of elements in here. If we do that for our zeros array, which we have initialized here, you'll see we get what we pass in here. So this what we pass in here is we give NumPy the shape, what do we want, and we say we want it with zeros or we want it with ones. Just a quick and easy way to fill the matrix for the array. Another way which is also kind of useful, especially if you think of, I don't know, iterations, if you want to simulate measurements, if you want to go step by step, so you can specify similarly to, you might know it from Python, is the word range 10. Would give you, of course, the range object, but let's do it like this. So you get the range of from 0 to 9 and so on. You can do a similar thing with NumPy. So let's say 1 to 10 in 2 steps. This is the equivalent thing which we get here. Just difference here is, of course, this gives you back an iterator, you can iterate over it, and this one will give you the actual array in memory. So you have an array starting from 1, 3, and so on. Criteria, start, stop, and the step size. This is, of course, useful for looping, if you want to loop over this as a variable in your experiments or whatever. And similarly, if you want to say, I want to go from 0 to 1 in 5 equally spaced values, then you would use the linspace API, this one. It would give you back 0, the difference of 0, 1 divided by 5, and then in steps until you reach n. I'm actually not sure now, did I think about it, what the equivalence would be in pure Python? Do we have something like this? We just have to calculate and just build it yourself, but yeah. So those are some ways to create initial arrays. You see, you can do it with ones, with zeros, with the A-range and linspace argument. There are a couple of features, and now let me talk about their dimensionality, because I think the NumPy array type is called ND array technically, I'm not sure. And ND stands, I think, for n-dimensional array. So the arrays in NumPy can have several dimensions. The special case of this one here was just a one-dimensional array up here, where we just have like one row with a couple of elements. If you think of a 2D array, this is essentially a matrix. So how we do it, we can pass it on here. So you say NumPy array, and then you pass on a list of, for example, 2 further lists. So this would be 2 rows in your matrix. And then you get your NumPy matrix. So here you can see, we can print also the shape. The shape we see, it has 2 rows and 3 columns. And you can similarly access each element by indexing the row and the column. So go to row 1 and column 2. So row 1, column 2 should be 2. We get that? No, what did I run? Wait, where is row 1?
0 index.
0 index, thank you. Yeah. Thank you. Exactly. So then we're right. And then we can do the same with the 3D array. So essentially the same thing as we did up here in 3D. Essentially we stack. So this one would be, in a sense, it would be just one matrix. If you think of this like one matrix and you stack another matrix next to it, another. So you get the 3D cube, so to say. That's how I call it. I think it's the standard way to say it. And you can do the same thing here. So you have your cube. You can see now the shape gives you back the 2 blocks of matrices, the 2 rows, and the 3 columns. And you can similarly also access, again, by accessing block, row, column, the element which you want to get. That's a to-do for me. I did not commit that yet. I think this is not in there. So just like a summary, it's also like a couple of nice ways to inspect your NumPy objects are n dimensions, which gives you back dimensionality. For the matrix, it should be 2 dimensions. The shape, which we just talked about, and the size. Size gives you, similarly to Python list, the length, the number of elements that you have in it. And you can see for a matrix we have dimension 2, and for cube we have dimension 3, and the size is 12. Another feature that is a bit different from Python lists. Did I illustrate that? Yeah, no, I don't think so. So if I do a Python list with, I don't know, 1, 3.0, none or something, this will stay there. So the types, so Python lists don't care about like the same type or something. In NumPy arrays, this is different. If we do a NumPy array of 1 and 3.0 and check the D type, it will be upcast to float, because this is a common data type in here. We can I don't know, put the 1 into a float and have the array here. This is needed for NumPy, I think, for the implementation somewhere. I'm also not an expert in the implementation of NumPy, but what I assume is that certain operations can be just sped up if you have the same data type, most likely. Right, arrays are fixed in size. What we can do with Python lists is something like this. So if I create one list, I can append to it and I can remove from that list again. So I can change this list. For NumPy, the size for the arrays, the size are fixed. What I can of course do, I can create new arrays and I can add arrays and I can create, I don't know, do some matrix operations on them, of course, but the array itself cannot be appended to in a similar way that we do with lists. This is one of the differences. You see that when I try to append here, it gives me an error that we don't have an append. Similarly to like, let me just check what we have. Yeah, okay. Indexing and slicing, I would say, is very different, very similar to what we have in standard Python lists. So we get the first element, we get the last element, we can access from, to, and can retrieve every second element. And this is also the same for a 2D array. This doesn't change here. So, and also 3D, we have a similar way we can access by specifying block, row, and so on. We can specify all in all blocks, in all columns, but row. In all blocks, all rows, but column 0, and so on. So access and array slicing is very similar. Where it gets more interesting is when we do arithmetic operations with the arrays. We have, for example, if we have our array here. Let's look at this for a second. This is our array, and we add 10 to it. So this will add to each element, not just like, I don't know, it will not just add maybe 10 to, it will not append anything, but it will add the 10 to each element. And similar, if we do array times 2, it will multiply or array times 2 square each element. So you can see we have 1, 2, 3, 4, so we have an array times 2, 1 times 2, 2 times 2, and so on. So these operations, essentially like a vector, you have like a scalar times a vector and you get the scale vector out of that. Then some things that can be quite handy is also again vectorized operations. If you just do the sum of the vector, the mean of the vector, you can get the sum of all the elements or the mean of all the elements that you have in your array. And one convenient way to interact with arrays is when you want to do not over all elements, but you want to do something row-wise or column-wise, you can use the axis argument. So you can sum along, for example, if you have this array here, you can sum along each column. So let's maybe do this separately. I don't know why I put this into all cells. Yeah, so if we sum along each of the columns, vertically you get 5, 7, 9. You can do the same with sum along the rows. And the difference here only is the axis parameter, so we do axis 0, axis 1. And then you get, of course, the sum of the row 1 plus 2, 3, and 6. We get 4, 5, 6, and 15. This is what we get here. And similarly, of course, with the arithmetic operations here. So we can also do the mean or, I don't know, rows or columns. Where it gets a bit more interesting, this is a very, very simple way to illustrate it. But this, of course, has a huge impact if you have larger data sets. So everything I'm showing you here right now are toy examples. It's very basic. It's very just to get in touch. And similarly, you can think about this one. So assume you have a large list, something like a large data set, right? What I'm doing now is I'm creating a Python list of the size 10 million and similarly a NumPy array with NumPy A range. Did I show you this before? Yes, I did, right? Yeah. So NumPy A range of 10, yeah, I should close the bracket, true. Then, sure, and same with 10 million, so we have a long array of values here. And what I would like to do now is I would like to show you just in this very simple toy example, illustrate what a nice thing about the vectorized operations is. So if you would, for example, say you want to square each element of the Python list from 1 to 10 million, each of them, you'd probably do it like this. In a very naive way, you would say for each x in the Py list, you go ahead and do x times 2. We're just going to measure the start time and the end time. We're just going to print out the time. So we took, I don't know, 41 seconds. No, 0.1 seconds. If you want to do this with NumPy, so we just have our array, our NumPy array here. Let's look at it again. Or maybe not, because it's large. We have a NumPy array which looks like this, and if you want to square each element, we just do times 2 on the array because it's a vector operation, right? And this is of course way shorter, but to visualize this at this time, it's like 35 times faster than for Python if you look over it, and this makes sense. So this of course is a very small example, but if you think, for example, this was the way I'm showing this to you, pandas can use underneath NumPy arrays. So if you think of very, very large data frames, very large data, where you do a lot of means and a lot of sums, a lot of calculations, then these things add up. And this is why we're actually showing you this. This is another way how to illustrate, another example for the loop time. So instead of just doing here, I just showed you the multiplication or squaring of each element. And here what I'm doing, I just want to add each element. Let's start with the Python example. Okay, I'm just creating 2 lists and 2 arrays. And what I want to do now is I just want to add each element. So each first element of list 1 plus first element of 2, and so on. This is what I'm doing here. For each index in my list, I'm going to go through and say list 1 at this place plus list 2 at this position. And similarly as above, I'm just going to measure the time, so just a bit longer. And if we want to do this with NumPy, again, as this is vectorized, you're just not adding, you don't have to think of adding each element, but you just to think of a vector addition. You have vector 1 plus vector 2, and you just, let's see. So this was again same order, 33 turns faster. And this again another illustration why this is beneficial. You don't look like you have questions. That's good, because now it would be the hands-on session of the tutorial. So I think I'm quite good in time. It was surprising. Just a very, very toy example. So what I would like you to do, if you want to, this is a chance for you, is the thing that I just showed you to do here, and this exercise is just plugging all of these together. So if you want, you can just go ahead and create a 2D NumPy array, call scores, and exactly. So what we want to do is we want to just simulate the scores of exams for 4 students. So you would have 4 rows. For each student 1 rows. You would have 5 columns, and for each column this would be, let's say, the points of the exam outcome, right? You can use NumPy, a NumPy function. I can just show it to you. It's actually kind of easy. Let's do it like this, just that we know what we're talking about. So each row gives you the exam output of 1 student, and each column is the score in maybe 1 specific exam. Maybe this is math, this is statistics, this is machine learning, whatever. And then what we want to do on these scores is we just want to analyze a bit. So this is a task for you where you can say, okay, hey, please, for example, print the full scores array. It should be fairly straightforward. You can also go ahead and print the scores of the first students. You can print the scores of the last exam for all students, and do certain aggregations on this one. So I would like to give you now some time to work on this if you like, and then we can look into solutions together and move on to the next part. Do you have any questions here? Doesn't look like it. Okay. So we can look over solutions together, or you can give me more time if you want. A bit more time? Sure. Already, like. You also make time. Okay. Shall we? Not like a huge deal. So, we already did this one together, so we did calculate scores, and the first task was to print the whole array. I think this is, we can do this. So let's just print the scores and the shape. The more interesting question is also, of course, what would I expect? Of course, what I put in here initially, this is the shape that I put in, so this is also what I expect. For our first student, the scores of the first student, so we think again about what we actually simulated here. We had 4 rows where each row was a student, 5 columns where each column was the exam. So what we want to access is essentially this first row here, if we want to access it. And this is how we do this. So scores of accessing will print first, scores of 0 will print the first row. If we want to, what was the question, print the scores of the last exams over all students, then we just want to access the last column, but all rows. And this is by, we can do this by in here. So this is how we tell it, hey, use all rows and just use the last column. Yes. So this is yeah, exactly. So this is the last column in here. So this would be the exam outcomes for one exam over all students. Then, if we want to get the average per student, this is a row-wise operation because each row simulates a student. Okay, so we need to use the access keyword 1, which is a row-wise. If you want to have the average per exam over all students, we use column-wise operation, so 0. And the overall our average would be just, over all elements would be the whole array, and then this would be maybe for the complete year of all subjects if we want to do this. This will conclude for this half-an-hour section the NumPy part. Do you have questions? Is there anything? I mean, as I said, this is a very brief introduction. This is very highlighted. What I did actually not go over at all is, and where NumPy I think personally gets interesting, if you, for example, are a scientist, if you use a lot of linear algebra and so on, they're probably also more specialized tool. I've never used MATLAB, but back in the days when I was still in physics, I did a lot of NumPy calculations with, for my simulations there. And now I'm not sure where I can find it. If I can find it, I think. Oh, yeah, I can find it. So NumPy also offers very excellent documentation. I really like it. And there was a very good NumPy tutorial somewhere. Did I just have it? Maybe it was this one. No. Ah, here, NumPy tutorials. Yeah. So I can recommend checking NumPy tutorials out if you want to just go deeper here, and if you also, for example, want to go over, you have maybe, I don't know, your own calculations, you want to simulate them. Not sure if everyone just doing deep learning, machine learning these days, if everyone just doing still measurements with linear algebra and so on. So this I can totally recommend if you have your experiments and you have your large experiments, for example, if you want to collect your data, love to maybe just do some standard analysis. This is where NumPy gets great. They have also specifically the linear, exactly that's what I wanted to show. The linear algebra package where you can do a lot of these matrix operations come in handy, and already quite a few things implemented, so you don't have to start from scratch. And of course, NumPy is the basis for all the, can be used as a basis for all the scikit-learn machine learning library interfaces and so on. So lots of things to explore, and I can highly encourage to understand NumPy more in depth. I also just did it for this tutorial, and I think it paid off. So I know more than before, which is a good thing. Right, so this would conclude from my end the NumPy part of this tutorial, and with that, moving on, we have roughly 1 hour left, so let's move on to pandas. So why pandas? Because NumPy was, or pandas initially was really just built in the start with NumPy arrays as backend. I think since 2.0 they have also had the arrow interface. I'm not sure if they support anything else right now. But in the beginning, Pandas data frame was really, I mean, it's mean to say, it was, I don't know, 10 years ago, it was a wraparound NumPy, maybe that was a bit mean, but it was a really cool way of accessing tabular data which used NumPy in the back to store it and to do operations on. So what do I mean with that? So before in NumPy we just had rows and columns and not a lot of like, say, visual way or user-friendly way to interact and to see. If you want to do simulate a more tabular style data, we can do that, for example, in Pandas with this. I'm creating a dictionary where each key of the dictionary could be the name of my column. So we have a couple of names here, we have ages, and etc. city gender. So there's just some data, maybe from a poll that I did or something. Maybe I just run around cities and I ask people how old are you, which gender are you, and what is your occupation, and I'm just trying to do some data analysis on that. So you will see, or maybe not immediately, but in a second, that each of these lists that I pass on here where the actual data is contained has the same length. And if I execute this, there's one way to call a create data frame is to say pandas.dataframe of this data, and you get your data frame. You can inspect it also. And you see, and this is very neat, and you can really have a nice view of your tabular data. So we have names, ages, and some names are mentioned twice. Some names are unique, but you can see that some of the cities are mentioned twice, Paris or 3 times, New York, London, Tokyo. So I traveled quite a bit for my poll, and this would be one way to create a data frame. Essentially tabular data. You can also use NumPy arrays directly, so you could just pass on your array. In this case, we just construct this array here, and just because we did it, why not do it again? So we have an array with the following shape, 3 rows, 2 columns. So each of these is a row and two columns on this one. And this is why we also pass 2 column names. So we can pass one of the columns as A and one of the columns as B. And this is what we get here. Or if we don't print it, it actually looks nicer. So it's our data frame. And DataFrame, when they came out, I remember I was a student back then, it was really, really cool because they offered a really nice interface to inspect, work with your data. So where you maybe prior had Excel things, you could suddenly just do it in your code and so on. So this was quite cool. And Pandas offers a way to, really nice ways to interact with it. So for example, you can just say inspect the first 5 rows. And in our case, this is maybe boring, but if your data is quite large, you don't want to just maybe a good way to just inspect a bit of it, not just get overwhelmed with it. You also get, for example, column info. So I think I should have removed this one. This looks nice if I do it. Yeah, okay, right. So we get what we actually have here. So we have a data frame about information about the index. So I didn't mention this one. So if you check the data frame again, we have, of course, rows and columns, and each of those rows is by name, and Pandas also adds an index. In this case, because we didn't specify one, when constructing the data frame, we can also specify an index. Yeah, here. So what I could have also done, if I would have liked it, I could have said, hey, please take name as the index, and then you would have accessed maybe certain rows by the name index, if this is convenient. As I didn't specify it, Pandas immediately added, or out of the box added a range index, and it's just the integer here. Right, so we get a bit of like information about the data type here. So we have object, integer, we have non-null, 12 non-null, so all our rows have no null entries and so on. You can also go ahead, and this is kind of neat if you have like a lot of numeric data, is just to get some quick stats. In our case, we only have age as numeric data. You get to count how many entries, the mean, the standard deviation, and so on, the interquartile ranges, whatever you need. This is nice to get a really quick overview of what is actually in my data, what is the distribution, and I personally use it a lot. If you want to access by column name, this is the syntax for it. So we do this brackets, and then we add the name of the column. something that I didn't add, maybe I'm just going to show it here. You can also, if you want to remind yourself down in the code in your Jupyter notebook, you don't want to scroll up, you can just say df.columns to remind yourself, okay, I also have a city column, so you could also access the city and get your column. What you get here then is, I think, a pandas series. Type. Let's do it here. Yeah, you get a series. So the series also has the index here from 0 to 11, so the range index. And when I go do values, you see what I have in here. The actual values are NumPy array. So let's do a type here. NumPy array. And this is what your series, I would say, maybe entails as like 2 building blocks: the index and the values. You can access your data frame now by label and index. So you do the log, you get the 0 row, the first row. If you want to access, you can also access the row by position here. Is this different? Yes, it's not different because we do have the same index. Yeah, would have been interesting with a different index maybe. And you can also filter those. So you can say, you can find conditions. So what you do here, maybe I should have broken this down. I'm just going to break this down a bit for those of you who have not worked with pandas before. So this is our series, our complete series. If I do, we have ages here. You can see there's an age distribution between, I don't know, 20 and 30 something. So if we do everything above 30, you get a Boolean mask. So this is a mask where it tells you where actually in your series or in the data frame, you can also apply some data frame, is this condition hit, age larger than 30. And if you now do this thing here, you filter your data frame for everything here. So you only get the entries where this condition here is true. And you can also change those conditions. So you could also do something like, no, this doesn't work here. Okay. Like this, and is it end? And let's do df of city Tokyo. Maybe. Let's see. Yeah. So now I can see that I also maybe for visibility I just changed 2 conditions. The first one was the age condition we had before, and now I also added city Tokyo, and then we can find all the entries that work here. So this is what we did here. Yeah, essentially changed 2 operations that I just had. Sorting values, I mean, there are like tons of these kind of features. So essentially, what I'm showing you now is how to interact with it, but there's a huge way, more than I can show you now in this 20 minutes. I'm just showing you like some of the important things, which you could probably also use from Excel. If you want to sort your values by age, you can define the order with the ascending keyword and get your data frame back as sorted by age. So this is 40 is above. If I say this one true, it should change, and it does, not surprisingly. So things get more interesting when we do aggregations, and the way we do that in pandas is with the group by argument. So say we want to group by city, so we want to say what is the mean or the average or I think mean age per city. And what we do here, I'm going to break this down again a bit, is df.groupby is the method here, group by. And then we say what we want to group by for, so city. So let's look into this one. And what this returns is, we can let's do something like here. So you'll see it just groups by city. So in the first data frame that I've printed here, just make it clear. Yeah. So this is our first data frame. We've grouped by city, so here we have all entries where city is London. The second one we have city New York, and then there's the city Paris, and so on. And now if you want to do something like, if you want to check the mean age for each of these cities, we can do it like this. So we do data frame group by city. We access the age column and we do a mean. And this is what we get here. Then we get the mean age per city, which is nice. And this is one of the standard operations you want to do. You don't want to maybe aggregate on certain column fields, do mean and whatnot. Very important feature. Everyone who deals with real-world data knows like missing data is a thing. So you can, for example, model missing data with a num. And Pandas then offers you ways to show you, okay, with the isNA method, where actually in my data frame do I have missing values? And then you could deal with it by either filling it, or you could also use this as a filter and say, please just give me the data frame where I just have complete columns. This is not what I wanted. DF missing, why doesn't it work? Okay, of course, yeah, DF missing. So, yes, not this didn't work. I'm not sure what I'm doing wrong right now, but this should actually. If I do this in series, this should work. Okay, let's do this one. Okay, it was considered a heck check what I just messed up. But here I just filtered for all of the, everywhere where the column A is NA, and you can also turn this around and say, please do give me all of this where column A is not NA, and then I see I get only those values. Probably there's also a way to do it for the whole data frame, I just don't know why. How. We could also fill them as a convenient function, to fill NA and or drop them. So we could do something like this. We just inserted zeros, or we just dropped them all. This is probably the thing that I'm looking for. Yeah, here we get there. Yeah. Another convenient feature is plotting data frames here, so we can just quickly plot ages of people and so on. So we can specify if I just do plot. It should just give me a line plot. Just do it in. Yeah, and if I specify what kind of plot I want and what the type should be, then I can give all kinds of arguments so that this one just passes through to matplotlib and creates a matplotlib plot. Coming to the end, and you're going to get a hands-on in a second. Just before we do that, we can just store and load our data to CSV, so we can store it as people CSV, and we should have that here. Maybe, just to be sure, let's do people too. Okay, actually, it changed. Need to refresh. It doesn't show up. Here it is, okay. Yeah. So we have people stored as a CSV and we can operate on that as well. Okay. So you've seen quite a few things, how to interact with the data frame, how to create them, how to filter by rows, how to filter columns, how to access it. Now it's again, I would say, a bit of time for hands-on. So I've just given you a very small sample data set where you have book sales, you have IDs of a book, a title, an author, a genre, and so on. And then maybe if you want, you can just go ahead and access this information here. So, for example, find all books in the AI genre and all of these things. So this would be the hands-on part, so I can give you, I don't know, 5 to 10 minutes, whatever you need. Do you need more time? Okay. Should we just go over it? Good. Very briefly, so essentially this was a summary of all of the kind of queries that you could do, and this is how you would probably use pandas the most. So just inspecting your data, querying it, and this is why the exercise is also concerned about this thing. So first thing was find all books in the AI genre. So we filter a condition where the genre is equal to AI, and which gives us those two books here. Similarly, if we want to filter for a price, we can say, hey, give me everything that costs more than 40. So we say a different column, integer or float value should work both. It works. The average price per genre, actually, good question, wait a second. Pandas. Average, just use the mean. Just mean, okay. So if I do group by genre and give me a column price and I say mean, then we get the average, the mean price per. Oh, what did I do? What did I do it? Here, exactly. So we group by genre. This is what we want to look into. We want to get the price, and we say, okay, for each of these genres, give me the mean, and this is how we end up here. Similarly, when we do total copies sold per genre. This is not a mean, this is a sum operation, but a very similar thing. So we group by, again, the genre, we look into the copies sold column. And as we want the total copies, we sum it up. And if we want to find the most expensive book per genre, we still keep the same condition here. We look into the price column and we say, give me the max of this one. So you see the group by is a way to interact with these sub-data frames that I showed you before. And this was just another kind of filtering exercise here, which is fairly straightforward. Right, so this would be pandas as a very rough introduction. It has, of course, also way more features, way more interesting use cases, probably, so I can say it. It is very basic, what I showed you here, but this is like to get you started. Do you have any questions at this point? Don't look like it. Which is fine. So then we're really good in time. Let's talk about polars. This is also the part that was most interesting for me because I haven't used polars before. I just looked into it for this tutorial. And after trying it out, I actually think I will for my own applications, for what I do. So polars is, I think, from the intended use case, they're very similar to pandas. So we also want to deal with tabular data. We want to interact with a data frame-like object. It is newer and has certain advantages. And the thing that is very, very much advertised for polars is its speed. It's very fast. It's way faster than pandas. I think last year, the year before, I think I saw a comparison against DuckDB and Dask and polars. And polars behaved quite well in terms of speed and performance. It was really cool to see. And the nice part is it's really just a pip install polars. You don't have to install a database, and it can do quite a lot on a large amount of data. So similar to pandas, we import polars as PL, and we create a data frame. This syntax here looks very similar to pandas. So instead of having pandas data frame, we create a polars data frame. We give it a name and we give it values. And here we are. Here's our polars data frame. This looks very familiar. Also, reading CSVs looks similar. So we can here do polars read CSV. The API is very similar to pandas. Pretty much the same. Now, when it gets to selecting columns, then we start like getting bit like a different syntax. So instead of doing accessing the columns in the brackets like pandas does, we have df.select, and we can select city and occupation, and then we get those two columns back. And similar to select, when we filter rows, we say filter, and we have a condition here. Now I haven't tried something out. Let me try this one out. But if this also returns a mask like in pandas, I'm curious. Not the view, but it says this is what it evaluates. It says here's a condition column age is larger than an integer here. And if we can apply the filter in a similar way. Anyone who does R in here? This is very similar to R, it feels, is it? Not?
I feel like the DataFrames, but I think it's a bit similar to data tables.
Okay.
It's also the fast version.
Okay, interesting. I just did R once and it felt somehow similar, because for example, we're going to come to it later, but there are like these chained operations.
Yeah, okay. This
which you have here. Yeah, right?
But I never used it.
Okay.
But yeah, it's typical R.
Okay. Right, where did I get? Okay, so we just did the filter operation. If we want to do the group by in here, it's very similar. So we say this is our column that we want to group by on. This is the mean, the operation we want to have, and we give it a different name. So the mean, this operation here is now stored as a column average age, and here we get it. So we get city and average age, similar to pandas. Now let's do this a bit more explicitly, because this is how I approach it. I know a bit about pandas, and for me it helps to compare it with the pandas syntax to come from A to B. For example, if we want to do data frame operations like adding things. So we have two data frame, two columns A and columns B, and I want to have the value of the row-wise adding, similar to NumPy, the vector operation. So A plus B should give me, I don't know, 5, 7, 9. And this is what we do in pandas, and in polars this would look very similar, right? So this is the same kind of syntax. We access the column here, and we add them. By filter and assigning, so when we have the same data frame again, we filter it with pandas we put in the condition here. And we do a copy, because otherwise we get the setting of copy warning, and then we say, okay, please add those two columns. And this works. And in polars, this is a bit different, and this is also, again, where I feel a bit like R. So we have a polars data frame, so we apply a filter. We do, here with these conditions here, do this adding and name it as C. And what we get. I also like the way that it's printed, kind of. Right. The aggregation, which is the important part, we have in pandas a group by, just to repeat it, we have teams, points, and assists. So the points per team, we can, what do we do here? Group by team, and we aggregate points. We do the mean and the sum, and the max of the assists. And we get here the mean point is 15, and the max of our points was 7 per team here. Makes sense? Polars, this again looks like a bit more like this chain thing. So we have this operation, mean of the points, call it points mean. Sum of our points, call it point sum. And the assists, the max of the assists. And this is kind of, I think, personally, in my opinion, this is kind of clean, and you just see what is executed in which way. I kind of like the syntax here. But the result should be the same content-wise. Now where polars maybe gets a bit more interesting is the lazy versus eager evaluation. So in pandas, what your default is your operations execute immediately. Just when you do the filter, it just operates. Do I have this one here? Yeah. So if we look into this data frame here, we just want to calculate some high scores. Okay. It is turned on. It's kind of bad for the stream, I think, if anyone's watching. Could you maybe call... Could you call the person maybe? I don't know. The mic isn't working. I think you can hear me, but stream people might not just now.
We can hear you.
Stream people?
Yeah.
Okay. Yeah, exactly. So lazy versus eager evaluation. What we're doing here? Exactly. Okay. So we have a data frame here. We want to get the high scores. So we do. Wait a second. I just lost my point. All right. Okay. Right. So we filter. Exactly. Okay. So we do first a filter of above this value here. We print our high scores and we evaluate this immediately. So now when we execute things lazily, this is where things get maybe a bit interesting. So you can kind of build your query or you can construct your query. You can say on a lazy execution, do the filter, do the group by, and do the aggregation. Now what is different here is at this point nothing is executed, like none of the filtering or something is done. It's just in plan, so to say, like a query plan. And this is also a neat feature I think. You can you can look into the query plan that you got here if you do explain similar to SQL. So, okay, we need to print here. So you see what this one is. This looks somehow nicer in my VS Code. Maybe I can show you here. Just run on. This looks somehow neater in here. Here. Okay, yeah. And you can see that there's a nice visualization on what's being done. So we first read the table, then we filter by the column and do the aggregation and so on, which is very much like the SQL explainer. This is kind of cool, I think. And if you want to actually execute the query, and so far we just had the query planner, just plan the query, we just do collect, and then we get our results. Okay. So this is all I had to show you about polars. As I said, I'm not a super user of polars. It's the first time I'm getting in touch. So for me, also the exercise was also kind of for me. And what I would like to do now is to add the same data frame that we used before, the people and cities and applications data frame. And what I would like to do is, if you want, we have a couple of pandas statements, pandas queries, pandas filtering operations, and so on. If you want, you can just take the time and translate them into polars operations. Now, this would be the last exercise for today. And after you've done that, I think maybe, I don't know, try out 5 to 10 minutes. Then we can just do a closing wrap-up, and it will be time for lunch break by then. slide's still not working. Okay. Let's go over what the results should be like, just very briefly, and then we can also wrap up. So I hope you have seen the main differences between polars and pandas. I hope I could motivate you. What I didn't do here, I think I should have done, is probably some example which illustrates the speed of polars. I hope you just believe me, it is fast. I just realized this one now. I just focus on syntax and how to do it and so on, and the lazy execution, which I like. But it is quite fast, and I think it's valuable to try it out on very large data frames. And when you have analysis that need to be time critical, I think you can really benefit from that. So when I did it, I just have actually an experiment running, which actually does a lot of these aggregations. I use DataFrames right now, and I might actually switch to polars just after preparing this polars. I find it quite cool. So this was a pandas code that we provided, or that I provided to you, and let's just go briefly over it just to wrap it up also. So reading CSVs is very similar to pandas. It is the same API, read CSV. You can do a select to access columns here. You can use a filter method on a condition to filter by age larger than 30, and you see you get the age is larger than 30. The group by is very similar. You get group by city and then chain it with the aggregation function that you want to do. In this case, how many people are in each city. You just count the name occurrence, so 3 in each city. Similarly to before, again, average age by occupation is, we then group by occupation. We select the column age, the mean, and call it, you give it a different name, average age. So that's how we would do that. And lots of these things, maybe I just skip over them because we have to end in 5 minutes. This is essentially variations of the same thing. Again, here, in lazy execution of the average age per woman, what we would do is we just go over and say, do the data frame in lazy, chain whatever we want to have after it, and then just do a collect. But this is also probably not the most interesting example. The most interesting example would be, I guess, when you have like a larger data frame and when you have more of these operations. So this was in short polars, very short. And this also concludes my tutorial for now. So I'm going to share the slides, but I really just have one last slide, which is a Q&A if you have any questions. So probably could also leave it away. Okay, so who's motivated to try out polars after this? At least one person. Thank you so much. Okay, who thinks that NumPy is more interesting than he or she thought before? Really, I think NumPy is really cool. So too bad that I couldn't transfer this one. Anything you would like to ask, discuss, also maybe something that you would like to see in a follow-up tutorial?
In the follow-up tutorial, I would like to see maybe usage of different way to storage data than CSV. CSV such as Parquet or the Feather, because they are more faster and more resource efficient than CSV.
Yes.
And maybe something about hard typing in the polars and memory management inside the application or inside the program.
Yeah, okay, cool. Just to maybe comment on that, so Pandas does support Parquet, so you can actually do in a similar way than you do CSV. You can do Pandas read Parquet. I just don't have a Parquet file just now, but you could do the very same thing. And of course, this is, as you said, interesting for compression, especially. You have columnar compression, which is really, really cool. And I just Googled because I wasn't sure, but yes, of course. So also Polars seems to offer a Parquet interface, so this seems to be fine. Exactly. So yeah, why not? I'm not sure if Marco Gorelli is coming. I think he was here last year. I think he's one of the developers of No, not this year. I know. Last year he was here, that's why, so too bad. He gave actually a detailed tutorial on polars last year at the NumPy. Maybe next year then. More questions or ideas? If not, that's also fine. You can find me here. I'm here all for the conference, and also if you want to discuss potential contribution, if you want to give a tutorial, go ahead, talk to me. We can motivate you to do something. With that, I would say thank you, and let's head over to lunch.
What I can send you this photo?
Can I give you my email address?
No problem.
You put it right here.
Thank you so much.
No problem.
Ja muszę ogarnąć. W sensie nie jest